Hi, hello. It is time for lecture 24, 24, or 42, 24 if your screen is flipped compared to mine. 42 is, of course, the answer to life, the universe, and everything. From what book series? Bet you could look that up too. But if you know it, without looking it up, send me an email. Get a bonus point. 1,000,000 bonus points. Up a letter grade. All right. It's great stuff. This lecture 24 builds on the concepts that we talked about in the previous lecture video, lecture 23, plus that other part, right? Diana Cowan's video about waves in general. And so you got that information about the waves and how waves work, right? So we are going to focus in this lecture about sound waves. Light waves we'll get much more into in the next course, Physics 2. You get a lot of light waves on that. Okay, but waves are important in general, and learning about both light and sound waves to start, just get the basics of what light and sound waves are like, are really useful because one is transverse and one is longitudinal, or acoustic, as they've called them. And as a result, we are going to focus on the sound part, right, which is the acoustic waves, pressure waves, longitudinal waves, like the kind in the slinky that Diana sent by going push, 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 right? As opposed to these kinds of waves. These kinds of waves we'll talk much more about in the next physics course, which is a great course, Physics 2. It's good stuff. But let's do Physics 1 and let's wrap it up strongly about sound, because I love music. I love listening to things. I love hearing people talk and to say cool stuff. Don't you? That's what we're going to finish up this lecture about. Let's remind ourselves those cool equations about waves, right? V, the velocity, equals F lambda. Now, Diana wrote lambda F, so I'm going to write F lambda just because that's what I'm used to. In fact, the lambda F and F lambda, same thing, so it doesn't matter. But the velocity of a wave is its frequency. That means how many waves pass any given location in a given amount of time, multiplied by its wavelength, right? The distance from one peak to the next peak in the wave, or one trough to the next trough in the other wave. So we're going to write that down, right? Velocity of a wave right? The velocity of the wave here is its frequency multiplied by its wavelength. Now, you have already known, as described in the lecture that Diana gave, right, that, or half lecture, I guess, because both of them together make up a whole lecture as a half length. But the frequency and the wavelength, you already know that generally speaking, right, the speed of a wave depends on what kind of wave it is and what it's going through, right? So the two speeds that you were really used to, that you were exposed to, I should say, in the previous lecture videos, the speed of sound in air, right? In air here in our world, right? At sea level is 343 meters per second. Like that, right? Give or take. Sometimes you'll see 330, sometimes you'll see 340. It depends on how hot the air is. It depends on how thick the air is. But 343, it's pretty close. I'm just going to use that number because that's a sort of a useful roundish number that people use. That's the speed of sound in air. And then there's the speed of light, right? And we talked about that, the speed of light. Now, the speed of light in air is almost exactly the same as speed of light in vacuum, all right? Or so I'm going to say the speed of light in air, and I'm going to use an approximation. In Physics 2, you'll learn the exact number. It's 299,792,458 meters per second. But to better than 1% accuracy, it's 3 times 10 to the 8, or 300 million meters per second. Okay, So the speed of light is way faster than the speed of sound. That's what you did in problem 3 of Diana's video, right? The time difference between something going super fast through air in sound or in light. But this sound thing is what we're going to talk about most right now for a couple of reasons. Like I said, we'll go much more about the speed of light and waves of light, okay? Because light also has a lot to do with even more of the cool stuff like electricity, magnetism. Light has to do with quantum mechanics and atomic physics and stuff like that. It's great stuff. We're going to get into that a lot, okay? But let's stick with the sound because let's wrap up with, like I said, hearing and music, which I love so much. And it's such a cool part of physics, and it's such an important part of medical activities. I know many of you wish to pursue eventually some sort of biological or medical career. And you know that hearing and vibration makes such a difference. Sound waves really, really matter in that. So let's go to the OpenStax textbook, and we'll just go through the key concepts that you should know about hearing, about waves. We talked about audial activity already, right? Auditory stuff, the anatomy and so forth. Now we're going to talk about the wave action, the power in sound, the energy in sound, and what happens when we use different frequencies of sound. Ultrasound, for example. You've heard of that before, haven't you? Yes, I've seen 3 beautiful ultrasound pictures of my babies, of my children when they were really small. You get to see something that looks like an ultrasound in this class. You may have already seen one before, but it's kind of cool to talk about, right? Okay, so here we go. Here's the textbook stuff. Here we go. So the first thing I want you to know, remember at the end of the previous Diana Cowan lecture, she talked about the Doppler effect, right? There's the Doppler effect for light, which again, we'll talk about in physics 2 a lot, but then there's the Doppler effect for sound. This is chapter 17.4, the Doppler effect and sonic booms, okay? And this is the frequency thing we're talking about. There's always that little ambulance showing here, right? Depending on how loud the sound is, relative motion to the source and things like that. This is a very interesting drawing where the authors decided to do about a person running sideways as opposed to the car zipping by, which is okay. So here's the information, all right? This is the equation that you should plan to use. And it turns out that Doppler effects are very, very useful for things like figuring out how fast how fast blood is moving in a vein or an artery, actually. It's really very cool. It also is, by the way, a way that you can use radar devices like police officers to figure out how fast you're going. Or things like when you see your speed, whatever, on the side of the road in a sign. That's nowadays such easy technology that you can just stick it right in the street sign. So it's pretty inexpensive and it's pretty accurate. So be ready to use it. But here's the sound Doppler effect. Okay, the frequency observed, that means the pitch you hear, right, from something that's emitting sound that's moving at a speed, can be shown to be, right, the frequency that's emitted by the source multiplied by this fraction, okay? Now, the velocity of the source, how fast it's moving, if it's moving towards you, right, then the plus sign is in effect. If it's going away from you, then the negative sign is in effect, is moving away at a negative velocity. Remember all that direction and magnitude stuff from early around the semester? Booyah, that kind of thing, right? So this is an equation. You can also use this kind of equation. It's basically the same thing, right? But notice that you can use the frequency of the observer is equal to the frequency that is emitted by the source. So what is heard here is what is made here multiplied by this fraction. The speed of the wave, in this case, the sound wave traveling at whatever, 343 meters per second or thereabouts, plus or minus the velocity of the observer, how it's moving compared to the actual velocity of the wave itself. You can see how this fraction is very easy to calculate as long as you know what's going on. So here's your example of a wave horn. Now, in this case, they use, the authors of this textbook use a speed of sound of 340 meters per second. You see the 150 hertz horn is kind of like about that note, maybe a little bit higher, like that. Okay, so will it sound like or will it sound like that, depending on the shift of the Doppler shift. So you should know how to do this. And that's why aside from the fact that the way that you can easily know whether or not a train is moving towards you or away from you, like it's getting louder, of course, right? That's the intensity of it because the sound is being produced closer and closer to your ear. But beyond that, the additional aspect is how high pitched the thing is. If it's higher and higher pitch, then it's coming toward you. If it's lower and lower pitch, it's moving away from you. Okay, just so you know. It's a very interesting kind of concept. So here are the solutions, and you should know how to make these calculations because they're very useful. Now, this sonic booms and bow wakes and stuff, this is cool, but it's mostly about like supersonic aircraft and stuff. So you don't have to worry about that so much. Don't worry about this because it has to do with shock waves, which is a very cool aspect of fluid mechanics, which we can talk about in the future. Like if the speed of an object moving through a fluid exceeds the speed of sound in that fluid, then you wind up with a shock wave and sonic booms and, cool things like that, which are really fun to see, but you don't have to worry about it too much, okay? But the Doppler shift stuff for sound, in this case, this example 17.4, these equations 17.20 and 21, very useful and very good to know, okay? All right, now, if you're talking about music, right? Remember we're talking about the vibrations of something in a column. Here's my water bottle. I don't know. Let's see if I can do this. Ooh, I don't know if the high pass or the low pass filter blocked out that noise, but what did I do? I blew air across the top of my trusty 1 joule's worth of energy every time I drop 1/5 of a bottle of water 1 meter distance, right? That's my 1 joule that just landed on kinetic energy. But it actually has this air column here, right? This air column right here. So if I blow across it, right? And in my mouth, I try to keep my mouth kind of steady as well. What'll happen is that the air, the wave will bounce in and out off the bottom of the water and around the sides of the container, and it will vibrate and create a sound that will then exit the bottle through the sides and up the middle, just like that tuning fork did. But that tuning fork is a piece of metal. Let's see, where did I put that tuning fork down? I put the tuning fork down somewhere. Oh no, I hope I find the tuning fork. Oh, here it is. It's my favorite tuning fork, so I don't want to lose it. But if I hit that and let's see, I'll just listen. I don't know if you can hear that. Right, that note, that A, right? The vibration is in this column and it vibrates a little bit on the surface of that jar. Now here I'm getting this thing to vibrate and it creates a standing wave, it's called, and creates a tone that you can hear. All right, now, what do you think would happen if I drank all the water and I blew the note? How would it sound? I'm not going to drink it all, but let's drink a little. Let's see if I make a difference in the note. Turns out that my mouth shape can affect the tone even more than the amount of water that I drank out of it, right? So a flute or a trumpet or a water bottle, those kinds of things, a clarinet, those are the standing waves in an air column that will produce these things. Now, I know they have openings on the bottoms and they have these valves on the sides, and all of those things change the way that the waves of that move around in the musical instrument do their thing, and their vibrating velocities and their speeds and how many frequency, how many times that air will bounce up and down, given the amount of speed that air, sound goes through air, and then how it produces the sound coming out. So like a good wind player will be in tune because they'll move what they call the mouth thing, the embouchure, like that, right? And that will make your tone better or worse or more accurate or less accurate based on the music. And it's all music and harmony and things like that. So that's a lot of fun. Anyway, this chapter 17.5 basically tells you a little bit about that, right? Constructive and destructive interference to cancel, like noise cancellation stuff. Remember I was telling you about that? The high pass and the low pass filters and so forth. How to make noise can't cancel. It's because when you have overlapping waves. Oh, look, it's a tuning fork. Not as nice as my tuning fork. It's just a drawing of a picture on a page of paper or electrons. So, electronic page, no big deal. But this is how you make the volume to vibrate, right? And how that works. And so these standing waves, it's fun to read. This is a basic fundamental, and then you have your first overtones a little bit higher, and then your second overtones higher, because the standing waves have more little pieces and they have nodes and things like that. Okay, if you like music, if you like thinking about how you make music, whether you're singing or whether you're blowing through some instrument or whether you're strumming a string or whether you're dragging a bow that has rosin on it across a string in order to create a kind of a violin or a cello or something like that, this is a cool thing to read. I think you would enjoy reading this chapter, so you get a sense of how sound is produced. And then, of course, you have these kinds of drums, right? This kind of marimba, where you have all the different tones, just like having those water bottle column that I was just blowing in earlier. But now you've got these cool jugs, and they use the gourds as resonance chambers, and the sound gets louder when you have a larger volume in which to ring, right? So you have all that, which is super cool. And I really encourage you to read through this chapter if you want. We already did 17.6 a little bit, so I want to go to 17.7, ultrasound. Yes, ultrasound. And that is a picture of some little not yet born individual in a uterus, presumably of a human being. And there's a little caption here that says thumbsucker. Can you see how this hand back here, which is kind of back over here, is reached up to the mouth here, and the thumb is being sucked? Yeah, that's kind of cool, right? And you can read this. This is the head. You can see some ear action over there. Ooh, there's probably a stapes bone in there somewhere, or a hammer and an anvil and a stirrup. Anyway, here's a body, and then that's probably a piece of the body there, maybe a knee, and maybe that's another, like a leg, maybe that's the knee. Anyway, if you're trained in reading ultrasounds, then you'll know what is going on in this picture. Right? And you can diagnose a wide range of disorders just from this. If you do a proper ultrasound, you can actually, for example, measure a nuchal dimension. I can't remember exactly how you do it, but it can help determine whether or not there's a possibility that the fetus has not Alzheimer's, the other thing, Down syndrome. Yeah, that kind of thing. So you can really find out cool things, and you can also see, something's not forming quite right, or almost all the time, yeah, things are doing great. It's just a nice way to take a picture without having to jab needles into anybody or cause any problems, which might have these issues, right? So how does ultrasound work? Well, if you want, you can take a needle, stick it into a tumor, like drill a hole in your skull, for example, stick a big needle in there and vibrate it so hard that you cavitate and you create energy so much that all the vibrations basically break up the tumor into little tiny pieces, which you can then vacuum out. Now, this looks like a skull, like a brain tumor, but most brain tumors don't actually look like this. Brain tumors, well, some of them are like well contained and like this, but a lot of them, like glioblastoma, some of the most dangerous, the deadliest tumors, they grow like into the spongy fatty material of the brain, and therefore you actually kind of have to suction them out very carefully. It's a different thing, but this is you get the idea of how you do this. You can also do this with like kidney stones and things like that. But the amount of power of energy in these things is what's important, right? And that's the last thing we're going to talk about in a minute, how much power you can do. But the ultrasound in the medical diagnostics, it depends on this thing called the acoustic impedance. That means that the amount of sound, right, the speed of an ultrasound wave, right, is dependent on the density of the material and the impedance of the material, how well it blocks sound waves, literally, right? So air doesn't block sound waves all that well. It doesn't have a very high acoustic impedance. But water, which is much denser than air, right, has a much higher speed of the ultrasound going through. Its acoustic impedance is much higher, right? The acoustic impedance of air is only a few hundred. This is over 1 million, right? So all of this like solid material, generally speaking, because it's denser, has a much more acoustic impedance. Muscle, fat, blood, water, bone. I mean, look at bone. It's many times, many millions acoustic impedance in these units, kilograms per meter squared second, as opposed to kilogram per meter squared per second, I guess is the right way to say that. We have compared to air here. So this is some, and so if you're doing ultrasound, what you're doing is you're taking this thing, this transducer material, which has a really, really high density and a really, really high speed of ultrasound that goes through it, right? And thus a high acoustic impedance. And then you take that, you generate the sound at a high frequency, so high that it can't hurt the ears, right, of whether people around you or the fetus inside the ear, which is still developing. And then if you send it in, and it basically echoes back, right? It bounces and bounces back. And whatever you reflect back depends on how much acoustic impedance the material has. And so you can pull a picture together and you can figure out what it looks like, which is kind of cool, right? Now, this kind of ultrasonic beams, like, a thing that like does the entire abdominal region, but you can also do it like with a handheld thing, like a little wand where you kind of poke around on the abdomen these days. These days, I think, back in the olden days, you had to put this like cold, sticky gel on the surface of the skin when you're doing this kind of abdominal ultrasound. Nowadays, you don't even need that in a lot of cases. Ultrasonic images can be done just by poking with the probe without having to put sticky gel stuff in there. So that's really kind of cool. Anyway, bottom line is ultrasound can reveal a whole lot of cool stuff. It can even make three-dimensional pictures, right? And it's really fun to look at. And you don't have to rely, you do just for obstetrics or gynecology purposes here. This is example by doing an ultrasonic image, but you can also measure the Doppler shift at the same time, right? We're just talking about Doppler shift of sound. At the same time, you can measure it and you can see that a bluer color suggests that it's moving more slowly, and a redder color means it's moving fast. What does this mean? Blood has to move faster through a constricted blood vessel, right? You remember this, Poiseuille's law, right? We were talking about that before, in Bernoulli principle. Yes, that's from a few lectures ago, right? Yes, you can do that. And the way you measure it is through the Doppler shift, through an ultrasound of a blood vessel. You can figure out blood flows and stuff. Is that cool or what? Right? Calculate the velocity of blood using Doppler shifted ultrasound. And then you can get a sense through the Poiseuille's law and the other stuff that we were talking about before in the semester about how much constriction there is and things like that. Oh, this is great stuff, right? Bottom line, I want you to sense and understand that applications of ultrasound, right, is really, really important. And this is all waves that are moving in a way that's, shall we say, very ordinary, very normal. Ultrasound is a high frequency, but it's not a lot of energy, right? And then like when we're hearing Doppler effect, we hear it all the time when cars go by or trains go by or anything goes by, even a person. Someday ask a friend of yours to go ee and then run by. You can hear the pitch change as they go by. It's really kind of funny, but enjoy that, so now physics is behind all these things that you've been experiencing your whole life. Right, and that Doppler effect can easily be calculated because you understand how velocity of waves have to do with the pitch of the waves as they go by compared to you. Okay, so the last key point that you got to know about sound, right, especially if you're doing biological purposes, is decibels. How loud is it in your ear, right? Now, decibels are a sort of shorthand logarithmic way of figuring out how much power is going into your ear. Okay, so if you multiply something by 10, you get an extra zero at the end, right? So if you're talking about things with very large scales, like say a trillion times, right? Say the smallest amount is like a trillionth of the largest thing that you can hear. That's kind of, you don't want to write out all 12 of those zeros, right? So you use logarithms to try to scale those things out a little bit. That is the nature of measuring sound. And it's named after this guy, Alexander Graham Bell. Remember him? Yeah, in 1876, he is a scientist who was trying to help deaf people, hard of hearing people, be able to hear better, like using electricity to amplify noises and sounds. And by accident, he was able to figure out how to transmit sound through a coding of electrical signals that get basically what we know today as a telephone. Pretty cool. We'll learn more about that in physics too. That aspect of translating sound into electrical impulses and then back into sound at a distant location. Okay, that's for later. But the point is the bell is named after him. Okay, if one sound is a bell, B-E-L, not B-E-L-L, although Alexander Graham Bell's name is B-E-L-L, to try to avoid telling the difference between a ding-ding-ding-ding bell and like a loudness bell. If something has 10 times more power hitting your eardrum, okay, 10 times more joules per second hitting your eardrum, then it's one bell higher in number. So, for example, if the threshold of human hearing, okay, is this much, and let's say a loud conversation is 1,000,000 times, all right, 1,000,000 times more power hitting your ear, Then let's see, it's 1 is like barely threshold of human hearing, and a million is 6 zeros. So 10, 100, 1,000, 10,000, 100,000, a million. So that's 6. So it's 6 bells higher. Interesting. Get it? Anyway, we human beings prefer to divide it up not into bells, but decibels or decibels. Okay, you've heard that one before, right? And so instead of saying each time you're 10 times higher in power means you add 1 bell, what you're doing in this case, you add 10 decibels. Okay, so the addition of decibels makes it easier to distinguish between small and big because you add sounds in between. So there's something like 25 decibels instead of 2.5 decibels. But that's just sort of how it's happened in our lives to use the power, how many watts, right, joules per second, every square meter of space receives in sort of sound power when these waves are hitting you, all right? So our eardrums are very small, right? They're only about 1 square centimeter. So that's 0.0001 square meter. And therefore, decibels, right, allow us to get that sense of how much power is hitting our ear in actual joules per second if we divide the joules per second per square meter by 10,000. Okay, so the explanation in the textbook is good. So I want you to see that. And this is, this is like the last thing in this lecture that I really want you to make sure that you get. So make sure to read this more after we go over this. All right. And there's really nice sort of graphics and explanations about sound and power and sound intensity. But this is the key equation that we're talking about here, right? Beta, the sound intensity level in decibels, is 10 times log base 10 of the actual intensity in watts per square meter divided by I0. I sub 0 is the reference, which is considered the lowest intensity of sound a normal person can hear at a note which is 1,000 hertz. 1,000 hertz is about 2 octaves above middle C. So middle C is like bong, and then 1 octave above that is bong, and then above that is, like that. So about up at that note, which I whistle, maybe even an octave higher than that, actually. Depends on what I'm trying to think of. Yeah, I think it's an octave higher than that. Yeah, up high. So go to a piano, hit middle C, and then go up 2 more octaves. Like the B just below middle C is about 1,000 hertz. Okay, so at that kind of highish pitch, if you can just barely hear it, then you're actually getting 10 to the minus 12, 1 trillionth of a watt per square meter. Okay, a trillionth of a watt per square meter. Divide that again by 10,000, right? So 1/10,000th of a trillionth of a joule per second hitting your eardrum as a whole is barely audible. Can you believe it? Our human ears are that sensitive? 1/10,000th of a trillionth of a joule per second of energy, and we can hear it? Like 1/10,000th of a trillionth of this energy that just hit my hand from this joule, right? That is enough for us to be able to hear it. That is amazing. Our ears are incredibly sensitive and so important and so worth keeping care of and keeping track of and taking care of and all that stuff that we do with it, right? Because I love listening to music. Of course, I listen usually to things that are a little bit louder than that, right? And basically, every time you increase by a factor of 10, right, reduce, add a 0, basically, or take away a 0 after the decimal point, add a 0 before a decimal point, 10 to the minus 12 watts per square meter. You add them, you get 10 decibels up. So this decibel number doesn't have to add so many zeros, but you can tell that it goes up in a hurry, right? So the rustle of leaves is only 10 decibels. Here at home, typically, you're hearing like some noises outside. You might hear television in a different room. You might hear some water running or something like that. That's all very quiet, right? It's about 30 to 40 decibels. Once you get to soft music and normal conversation, kind of like this, it's about 60, right? Now, if I had like an audio volume thing turned up, if you guys turned up my volume higher, if I'm in a classroom lecture and I had a microphone attached, and, loud noise, that might be like getting pretty loud, 70 or 80 decibels, right? That's right about as much as you want to hear comfortably. You don't want to listen to this much more than that, right? So if you've ever seen it, you want to keep it at about 80 decibels. You don't want to go much higher than that. That's already way high, right? That's 100 million times more power hitting your ear every second. 100 million times more power, right? 100 million times more energy hitting your ear every second from these sound waves than the threshold of human hearing. So you don't need that, right? And then if you go even higher, now you're having some trouble. Like 90 decibels inside a heavy truck, or say a lawnmower is usually about 90, like a quiet lawnmower, really. And you can, if you hear that for hours and hours a day, like if you're like a truck driver and you don't wear ear protection, or your cabin is not well insulated for sound, or if you're like a lawn maintenance person, like you mow lawns for a living or something like that, and you have a leaf blower around and you have a lawnmower going and things like that. If you don't have your ear protection, you might actually wind up damaging your ear over long periods of time, right? At 100 decibels, we're talking really loud, like a siren, right? From an ambulance or something at about 100 feet. And if you get exposed to this 8 hours a day, not too long from then, it wouldn't take very long, days, weeks, months at most, and your hearing is going to start hurting. Now, at 110 decibels, right? That's getting loud. Now, 120 decibels, they call it a loud rock concert. That's like if you're near the speakers, right? But 110 is already pretty loud, okay? Most like DJs on the dance floor in a club, or at say a wedding reception or something, is already 110. So that's pretty big, and you don't want that much exposure for that. If you're just getting 30 minutes a day, that's plenty to hurt your ears. So don't do that, right? I mean, I myself am perfectly happy to enjoy the beat with like lower sound, but that's just me. Even when I was younger, actually, I liked the energy, but I didn't need the volume because it hurt my ears. And I like listening to music. I don't like just hearing loudness. I like to hear the variations and the subtleties. And so as much variation in the strengths and the differences and the frequencies and the pitches and the voices and stuff was really valuable to me. I like that. And then here, scary stuff, okay? If your ears are hurting when you're listening, that's 120 decibels. And if you get even higher, if you get a few thousand times that, you're going to hurt your ears, period. You're going to need some surgery or get some really repair. So you want to be really, really careful about that. Anyway, that's how you measure decibels. This is the equation you use to measure decibels. And it's good to know, right? How loud are things? And so you can, in the future, always know, that's what a decibel means. And that's where we want to keep things. Ideally, you always want to keep, if you can, your listening at 80 decibels or lower. I myself prefer it to be about 60, but it depends on what you're listening to at any given time. There's a lot of cool stuff in these these college physics chapters, right? That we are not talking about very much, just because that's sort of where we don't need to go into that much detail at this point. All right. So let's see here. I think that will do it. I think I'm just going to write down. I'm just going to write down this equation, right? This is the intensity in decibels, 10 times the log base 10 of I over I naught, where I naught is the threshold of human hearing. Threshold of ordinary, I gotta say, because people, of course, have different human hearing. Right? Remember that this is a very useful guy. It's not that hard to do, right? Because all you need to do is take whatever intensity you have, take 10 to the power of some number equals that intensity, and that to the power of, right, divided by or subtracted from 12 because that's 10 to the minus 12, right? In that case, is the threshold and is how many decibels it is. Anyway, this is something that you will use a lot if you have anything to do in the future with things like sound safety, audiology, speech pathology, or, in my friend's case, cochlear implant surgery. Whatever you do, that's a useful thing to have. Okay. Well, that brings us to the end of lecture 24. And lecture 24 is the last lecture of this term for this course, Physics 1. That's right. We have gone through the first part of the kind of physics that will be useful to you, that will be meaningful to you, that will be valuable to you as you go forward in a career that might have something to do with, say, biological sciences or medical career or veterinary or, something like that. Biologically interesting stuff. Think about what physics you've learned. What is the key stuff that you've done all semester long about motion, right? About things that move in a straight line, things that bend, right? Like your back, things that spin. And then you learned about things that get hot, that jiggly wiggly wiggly thing, right? Heat and fluid, things that flow, the motion of things like gases and liquids, blood or air, breathing, pressure becomes important, right? And then we go forward from there to understand vibrations, which can create pressure like waves and store energy. Energy is knit through it all, right? Energy is the thing that powers phenomena. And some of that energy is free to do work, like lift water bottles, right? And then some energy is not free, but it's still part of the total energy involved. And then sometimes, depending on that energy, could be stored like in the vibrations of the materials or in the order or disorder. Remember that entropy thing, the laws of thermodynamics? You can't win, you can't break even, and you can't get out of the game. That's physics, right? You use a little bit of math to figure out how these numbers are calculated. And from that allows you to just take random pieces of information and turn them into useful and meaningful and valuable and powerful tools, theories that help you understand it, right? And therein lies that last key part, which we've been going to all semester long, all term long, about facts, data, laws, hypotheses, and then making predictions based on the hypotheses to see if you're going to falsify them or whether they're confirmed. And then you cycle them all over again, knowing the difference between a non-scientific theory, which is totally fine, from a scientific theory, which you can use for scientific purposes, and pseudoscience, where they pretend to be a scientific theory and try to convince you that it's gone through all these steps when in fact it is not, right? And so that kind of understanding what science is leads to your understanding of physics, because of course, physics is the poster child of science, right? If you want to learn something with the scientific theory, physics is the way to go. Starting from very beginning, what makes things move, all the way now to where we are, why can we hear, right? What are the things involved? It's beautiful stuff. I hope you learned a great deal. Remember, of course, to be filling out your study guides throughout. If you have any questions, ask me, ask your recitation instructor, ask your lab instructor about all this stuff. All of this has been knit together in such a way for you to get a good introduction to the physics of the universe, of the world, of the human body. And in Physics 2, if I should be so fortunate to see you there, you're going to get some great, even more cool stuff, right? Maybe not cooler than this stuff here, but just more cool stuff. There's so much that I can't wait to share with you. It is the best stuff. It's awesome. It's so much fun, and it's so much power. It's so much knowledge. It's great. Thank you for going on this journey with me over the course of this term. I hope we'll see each other again down the road. As always, any other questions, anytime you want, feel free to contact me anytime. Happy to chat with you about it if I possibly can. And I hope that our paths will cross again as we learn more about the physics of everything. Thank you so much. Have a wonderful day. Talk to you again soon, I hope. See ya.